So, well, as you perhaps may recall, we started, or I did my best to introduce some other technique which I will be relying a lot in this course, and these are variational principles. And in here, yeah, so here's the motivation which I already summarized last week. So I hope it's not really necessary to repeat it over. But what is nice and convenient thing is that we can basically formulate this variational principles in a way which, at least to my weird way of thinking, sounds to be natural, and it carries some nice physical sense. By that, I'm not claiming that the differential equations cannot be interpreted properly, but somehow I find it more elegant, and certainly I'm not the only one who sees it in the way. So the argument was that instead of prescribing this primary coefficient, I introduce a certain local function which is attached to a certain point x, and some vector which I call s, just to use different ladder. There is no clever strategy behind that. It is a quadratic function of this s, and the constant in between these s's is the L matrix located in a given point. And depending on your interest, this physical problem you are concerned with, this W has a meaning of energy, which is stored, and its energy density. So this is something which is stored in the vicinity of your point. And well, I'm claiming that by actually prescribing what this W is, I'm giving full constitutive response, because my claim is that if I differentiate this W with respect to the second argument, I'm getting constitutive relation. And if I differentiate the potential twice, I get the stiffness-like coefficients, if you wish. Okay? So in another word, if I take the gradient of this W with respect to the second argument once or twice, what I get. So sometimes people like to say that flux is a gradient of a certain energy density, and actually this constitutive parameters, they correspond to hash. I also was trying to put forward that because of the properties of the second derivative, actually this matrix L has to be symmetric, which was strictly speaking not needed or before in the PDE approach, but it has really some good physical grounds. And the second condition was that if I have a look at any point within my body, and I would like to store a certain amount of energy by setting this S to be non-zero, and again, this S has a meaning of temperature gradient, for instance, I need to get always the positive number, with the only exception when there is no temperature gradient, where this is zero no matter what is done. So this is, well, a principle which is very consistent with some basic thermodynamic considerations, which actually says that, well, my body cannot spontaneously produce energy. It only consumes it in a way that I need to store certain energy to initiate some temperature, some heat flux phenomenon, or deformation of the body in elasticity, for instance. Okay? It also implies simultaneously that this L, this matrix of primary coefficients, is not only symmetric, but must be symmetric positive definite. So it also gives some mathematical structure to this first coefficient. So then we define something which is called primal variational principle, which says that for any field E, I will actually have a look what is happening in terms of its value in any point and in a given position, and I'm integrating that over the body. So this gives me actually the amount of energy which is stored in the body if this is subjected to a given distribution of my quantities of interest. And again, I would like to reiterate that in my favorite formulation, here I'm saying that I'm just working with gradients of my primary variables. And I also, spend quite some time in that PDE viewpoint by saying what are all admissible fields I would like to work with. And I would like to remind you that I introduced this calligraphic E omega D, which actually expresses the physical condition that it has to be curl-free, this field, which means that it can be derived from the primary potential. And this D here stands for the fact that it meets the Richle boundary conditions. And unfortunately, unfortunately, depending on your attitude, it can be shown that in this particular case, the mathematics and physics just play nicely together, because under this very natural assumption, it can be shown that there is a solution to the problem, and moreover, this solution is unique. Final piece of notation which I have introduced is this Curly inequality, which actually says that the matrix is symmetric positive definite. Okay, so this was what I was trying to do first. Then I actually repeated the same story, presumably in a slightly higher speed, or at a slightly higher speed, in giving this dual variational principle. So this dual stored energy density is given by this particle expression. Again, this is the amount of energy you have to locally store in the vicinity of your point X in order to see the heat flux of the intensity given by this particle vector in there. And I will get that intensity variable and the dual coefficient by performing the differentiation once or twice, because this is function of multiple variables. I have to do it properly, but that's pretty much the end of the story. And I will also assume that this M of X is everywhere positive definite tensor, matrix, and I will just take the response of the full body by integrating these contributions, and hence I'm saying that from all admissible distributions of these vector fields, which are source-free and satisfy the corresponding boundary conditions, I actually I have to actually minimize the energy which is stored in the whole body, but this time this is this complementary energy. I also said that, in the, so two remarks. So first remark was that this is something which does not require quadratic energies in the second argument. The same argument can be done if these are convex, so basically everything holds. So you can treat some special kinds of nonlinearity using this framework. But for instance, the nonlinearity is not sufficient in order to describe finite strain elasticity, for instance. And the second second remark was based on the fact that actually I was a bit obsessed with the consistency condition at the very introduction of the course. And this consistency condition, which says that actually these two matrices for every X are mutually inverse. So in this language of energies can be expressed in the terms of so-called validity of Legendre transform. And I also said that if you would like to see it yourself, then this assignment is the right place to go. And in the very last part, I was talking about last property, which in my viewpoint is essential, which is orthogonality. You helped me what it means that the two vectors are orthogonal. You also helped me to say how I should define the orthogonality between two fields. I will just use this condition for any x and integrate, and if this really integrates to 0, then these two fields are orthogonal. And I concluded our session last week by saying that we will be working a lot with averages or mean values, which are just obtained by taking my quantity of interest, integrating over domain, and then scaling it by the volume of the corresponding domain. And then I I introduced this fluctuation of that function. It's also called centering, I guess, especially in probability and statistics, which actually means that you take your variable and you subtract the mean value or average out of it. So what remains is of 0 mean. So I can see that I can take any function and decompose it into the mean or average part and the fluctuation. And this is where I end. And just to make sure that I do not skip anything important, I will just take my notes from the previous year. So now, I have introduced these two objects, but before doing so, I was talking a lot about orthogonality. So what I'm now claiming is that the first example of orthogonality is as follows. So if I will have, with a slight abuse of notation, some vector, which actually represents a constant function simultaneously. So this is the function which for any x gives you this particular value. And I will have fluctuation of any function, so something which is 0 mean. So I'm claiming that these two are mutually orthogonal, or are orthogonal. Okay. And the argument proceeds as follows. So what I would like to investigate in particular is that I will compute this inner or scalar product between these two functions, and it now seems that I should do it consistently with the remaining notation. Oh, so here I have it correct. Okay, so if you just remember what this was previously. Yeah, sorry, here I forgot to indicate that I have this omega. So this was the definition, if you recall, this one. So what I'm now saying is that this is integral with respect to omega, just to pretend that I'm a very well organized person. I will just scale it by 1 over omega. The first argument will be this constant vector c, and it will multiply this f prime, where I would like to reiterate that this f prime is no longer derivative, but this is the fluctuating part. You can use different symbols. I experimented with a bunch of those, but eventually it turned out that this is the one which is most appropriate. So this is what I will have. So my f fluctuation as a function of x dx, okay. And now I will start the standard massaging of these relations, because I will say that this is x independent, hence I can transport it out of the integral. So what I will eventually get is 1 over omega times c transpose. And what remains inside is this fluctuating part dx. And I'm actually doing that only to realize that this compound expression, so this 1 over the volume of omega times the integral, this is precisely what I denoted previously as the integral of the as the mean value, Feldman pardons, of that function. But this was defined in a way to ensure that the mean value of fluctuation is 0. So this is what I forgot to say here. Perhaps I was too tired. So this implies that the mean value of the fluctuation becomes 0. And this just closes the argument, right? Because I have this C transpose multiplying 0 of the corresponding dimensions, which is 0, obviously. So these fields are always orthogonal to each other. Yeah, and I really do not recall whether I said that before or not, but this orthogonality actually means, in a certain sense, that what happens in this direction is independent of what is happening in that direction, right? So, or in other words, if I would like just to take this vector S and I will scale it as much as I wish, there is no way I will get this orthogonal vector, right? If this was some kind of oblique vector here, for instance, I can get a part of that by scaling that vector properly. But if this is just orthogonal to it, they are very independent. I don't know how to say it. So if you say about someone that is completely orthogonal to it, you just completely miss the point. And this relations actually shows that there is a same relations between these constant fields and fluctuations. They are just orthogonal to each other, right? So there is no way how to express fluctuation as a constant field except for represented by 0, but this is not really useful information. So any questions, remarks? Is this clear, at least to some extent? So, this is something which is rather trivial, but very useful quality. But this is not the main motivation why I show that, because what I'm claiming now is that actually I worked a lot with these sets, which I called calligraphic E omega and calligraphic J omega. If you just are writing these notes just following mine, then please leave some extra space there, because I have not been very specific about the boundary conditions. Okay. In principle, again, this E are curl-free fields and J are divergence-free fields. So I'm saying that actually these two spaces are orthogonal. Which is a shortcut for saying that if I take a space, arbitrary field or function from the first space, it will automatically be orthogonal to any field from the second one. And again, I do not know how much you have seen this argument, but after some time, at least from my naive engineering viewpoint, it turns out that all this linear or variational theory for linear PDEs or mechanics just bit in terms of certain virtual expressions. So it's all about by-parts fluctuation, right? So you have the differential constraints of the structure beneath. You can average. This is important very much for the for homogenization. But there is finally one additional very convenient tool, which is by-parts integration. Okay, and I would like to briefly remind you that, and I do apologize if you know it, and also it can happen that usually when I say think like this, I make immediately some very stupid mistake. So if this happens, that I really apologize. So by-parts integration actually means, in my viewpoint, that if you multiply two functions and one of them is actually a derivative of something, then you can equally express that by means of the expression where the derivative is transferred to the left-hand side. There is minus sign on top of that, and you have some information from the boundary of your domain, which in this 1D case are just 2 points. And I think that is right. So this is hopefully something you have seen before. So now, yeah, to fix the, to actually show what I mean by this, I will consider this scalar product between f of x, so this vector function, and g of x, also a vector valued function from omega. I would like to reiterate that actually this first guy is from this capital E omega, whereas the second guy is from this j of omega. And, well, I will actually, just for aesthetic reasons, not aesthetic, so sorry, this won't be aesthetic, just for the sake of explanation, I will actually swap what is written over there in order to express it in a more condensed way. But before doing so, I actually need to do one additional step, which I did wrong. So now we'll use the condition that this f is from E of omega. If you would like to write this x in there, just be my guest. And if you still recall, this says that there exists a certain function, which I will call f, which if I take its gradient, phi, if I take its gradient, I will get f. So if f equals to E of omega, this immediately implies that f is a gradient of certain scalar function, which I will call phi. And again, if you went through the first homework already, well, this can be, this is something which you can understand from simple examples, or you can even, just put forward an argument by this Holmes in general case. So what I'm saying is that because I know that my first field F is from this nice space, then I know that I can equally well express it as a gradient of a certain potential or primal variable phi, multiplying this g of x. And this is again the scalar product between two fields in omega. Okay? Now I do apologize for cheating a bit, but using this lecture format, I can pretend that I'm making no mistakes, which actually no one will ever believe me. But anyway, so I should have written it in this way. You can just imagine that, you know, if I just take this and swap the sides, I will get precisely the same result. So I just need to apply to this argument. So yeah, now I see what I did very wrong. But I can still use this distinction by letters. So, you know, from this 1D formula, this gray F actually corresponds to phi. Sorry, this is very unprofessional. And this G indeed is the G from my formula. Okay? And how I know that? Well, I know that because I can expand what is written here, and perhaps I should have done it in one step. And just recall that actually I defined this inner or scalar product in a way that I integrated over omega. This is the first argument. Because this is gradient, this becomes a column matrix or vector. So I need to do inner product or transpose this with this vector field g of x dx, right? So this just shows what I meant, that this is basically this part of the formula just written in multi-dimension. So what I will say would be as follows. So I will have this integral over omega with the minus sign, and I will have this phi of x multiplying the divergence of g as a function of x dx. So if you just would like to identify it in this one-dimensional formula, this is precisely this term, right? So this is what I have. So I got this original function in here, multiplied by the derivative of this g, and if you just write down what these gradients mean, etc., so if you just expand it, it actually can be shown that this is what you get. Plus, you get the generalization of this term here, and this generalization is nothing else than the boundary integral, and in the boundary integral, I will have the following expression. So I will have this 5 of x, then I will have this g of x in here, and this is pre-multiplied by this n transpose as a function of x. Where just to again do my standard sketch, so this potato is omega, its boundary is just here, and I would like to remind you that this n was something which I call, hopefully correctly, outer normal vector. Normal means that if I just have a look at my boundary, I will construct the tangent which locally approximates the boundary. This guy has to be orthogonal to it. And unit means that this is of length 1, its norm is 1, sorry, and this components of n are dimensionless because these correspond to some directional signs and cosines. Okay? So this is precisely what I get. And if you just think what this 1D formula actually tells me, it is precisely what is written here generalized to multidimensional case. So is this understandable, or was I too quick? Should I give a more detailed review on this bipartisan integration in multi-dimensions, or is this okay? I think this is okay. Perfect. So then, I said very boldly that I say that these two fields are orthogonal, which means that if I was not inventing things up, then actually this must combine exactly to zero, right? So now if I take this term, which is the divergence of G, I need to take into account that it is located in these functions J of omega, which, if you recall, were functions which were divergence-free. So because this J is in this divergence-free set, then actually this goes away. This divergence is zero. And hence, no matter what the value of phi is, this goes away. So actually, it turns out that the only term which decides whether this orthogonality will hold or not is actually this term. And now comes, what I always find a bit of miracle, because if you just have a look here, this is something which is obtained by integration from the boundary. And this is precisely when your boundary conditions jump in, right? By boundary conditions jump in. And moreover, actually, these boundary conditions are precisely in the right format, which actually say that, I have the product of two scalar functions. One is this phi, this potential from which the gradient is derived, and this is n transpose times g. And if you somehow, recall what I said, that this is of unit 1, it is actually nothing else that the normal component, so one value of my function j. Right, so this is actually the component which is associated with the normal direction. So it actually says, or only shows that without any other specifications of the boundary condition, actually I made the claim up. It is not always true. There must be a certain reasonable way how this can be satisfied. And basically, from that multiplication kind of expression, there are two main things how to ensure that this indeed integrates to zero. The first condition actually says that I need to say that my phi of x is equal to zero everywhere on the boundary. Which means that in addition to the previous conditions, meaning that this is the field which can be derived as a gradient of something, it must additionally satisfy Dirichlet boundary conditions, but not any Dirichlet boundary conditions, but the zero or homogeneous boundary conditions. Okay? The other thing is that I will say that the second component of that product, so this N transpose times G, so the normal component of any admissible flux I'm considering in my optimization problem. And sorry, I again lose concentration on the way. So these are zero or homogeneous Dirichlet boundary conditions, of course. Right? So I'm just saying that I will solve a problem with fixed boundary conditions. I also have the opposite case in which I say that actually the second part of the product, which is the normal component of my flux vector equals to zero, which corresponds to perfect insulation or friction-free boundary conditions. But in any case, these are zero or homogeneous. Neumann boundary conditions. Okay? So this is the other option. Now when I'm thinking about that, actually sorry, yes, so, you know, there's some relations to something I would like to show in the next lecture, at the very beginning, hopefully, is called parent properties. Sorry. I was starting to think about some detail, hopefully at least, and I completely lost the track. So what I'm now saying that if I'm considering the situation in which the boundary conditions are of the Dirichlet type and are of the Dirichlet type with zero on the right hand side, so I have Dirichlet boundary conditions, then actually these two fields are orthogonal for any G, so for any vector function I started with. So what I'm saying is that if this is zero, that no matter what G is, this will never contribute. On the other hand, if this vanishes, then this phi can be arbitrary, and its gradient can be arbitrary, and hence this holds for any f. Which just satisfies this differential constraint, right? So what I'm saying is that actually I can identify two situations. In the first one, I have the zero Dirichlet boundary conditions on the boundary. And then I know that this orthogonality holds for any divergence-free field irrespectively of the boundary condition. And then I have the second situation in which I'm assuming that my body is completely insulated. And if this happens, that no matter what the value of that what that f function I will take, it will be orthogonal only under the assumption that this f is admissible, meaning it's curl free, right? So this says or puts something very essential and I would like to conclude this part of the lecture by this. So there is something which is called Helmholtz decomposition, which is actually terminology which I borrowed from fluid mechanics mathematical book, where this is well known, and it took me really quite some time to find it. It was not because this is well hidden, but because it took me very long time to realize that the only thing I need to do is to ask Michal Beneš, and he gave me some nice book, and everything could be found there. So for that, and I do apologize, but I need to introduce hopefully the final set. So this is this capital H, calligraphic. With the subscript of omega. This H stands for Hilbert, because this is a space of infinite dimensional space of functions which have a certain structure which is inherited from the standard finite dimensional case. And again, this is a notation which I didn't invent, but I actually borrowed it from that book in Milton. In normal world, actually, these are just square integrable functions on my domain with values in Rd. If you do not know what this means, then just forget what I said. So these are just all reasonable functions I can think about, which give me. So these are all admissible intensity or flux field which give me finite values of energy stored in the body, roughly speaking. But again, this is highly optional. But again, these are all fields which I can work with, and again, they correspond to finite energy. This is nice argument. Hopefully, I was not speaking too fast. So these are all fields of finite energy. Yeah, this is nice. This is something I should perhaps elaborate a bit more next year earliest, unfortunately. Sorry, it hadn't occurred to me in the previous runs of this course. And what I claim, or what this Helmholtz decomposition claims, is precisely what I tried to explain by the previous argument, which actually means that if I take all fields which are this calligraphic E, so which are curl-free, are defined on finite dimensional domain omega, and I will assume that they satisfy the zero Dirichlet boundary conditions or homogeneous Dirichlet boundary conditions. So this actually represents these homogeneous boundary conditions. So these fields are orthogonal in the sense which I have introduced to all divergence phi fields, no matter what is the value of boundary conditions. And this circle and plus, this is something which is called orthogonal sum. And basically this means what this picture suggests, meaning that I'm saying that these divergence phi fields I can imagine, to be associated with this direction. These divergence phi fields are just orthogonal to them, so there's no way to compensate them. They are complementary to each other and things like that. Okay, so they just work differently. They just encode different physics, different considerations. If you like the drawing these four components diagrams, they are always on one side or another. So these are different beasts, right? And on top of that, again, these are orthogonal with respect to all the remaining ones. Sorry, this is divergence fields. And I'm saying that this is not the only split of that original space of all vector fields of finite energy. I can also say that I will take arbitrary compatible field, so the one which can be obtained as the gradient of certain function, scalar one, and this is directly orthogonal to J of omega, but with zero Neumann boundary conditions, right? So this zero actually says that this is exactly what I want. So there is, subtle difference, not really, well, it is essential, but it turns out that these differential relations or constraints are insufficient to characterize this orthogonality unless you supplement them with a suitable boundary conditions. And we'll come to that. So this is the first claim which I have just shown. And this is something which again is heavily used in mechanics of fluids mainly, because fluids are incompressible, and this incompressibility condition actually is related to saying that the divergence of something is zero, and this is used in theory and also in computations. In homogenization, there is we can also benefit from that a lot, but hopefully within something like 10 minutes or 15, I will start talking about some fluctuations and all things like that, and try to convince you that actually the only thing which I need to do is to compute fluctuation because of some some constant field. And in homogenization, there is also alternative and even finer decomposition, which combines these two examples together. So what I'm saying is that actually I can claim the following direct decomposition or orthogonal sum. And I will just write it down first, and then I just comment on what I wanted to say. So I'm saying that actually using that example which I started, I can decompose these functions of finite energy into three mutually independent contributions if I use these fluctuating fields on top of this differential constraint. So I would like to remind you that this is fluctuation. So I'm saying that all constants are orthogonal to these fluctuating fields. This is what I have shown before, just by definition, basically. So this was just to get you acquainted. And these two are mutually orthogonal to each other because shifting this value by constant, this does not change any of the arguments which are put forward. And likewise, I can do the same thing for the case in which I have full control of my boundary in terms of fluxes. So all boundaries are insulated, and the only condition on my first argument is that this is compatible. And again, because these are fluctuating, so zero means, then all are naturally orthogonal to all fluctuations. Again, in the sense of this scalar product I started with. So this actually is the final bit on the structure of the governing equations I would like to introduce. So this is the theoretical basis on which I will start building the additional results under the very brief assumption that actually I didn't forget anything. So if I will need some new stuff, I will just introduce it on the way, but perhaps this year I will just try to pretend that I have everything very nicely organized. But before doing so, there are two remarks in order. So the first remark is related to the fact that actually after I will finish the second, so the subsequent lecture, I don't know how many weeks this will take, but then I'll try to argue that actually, although this cannot be done computationally, actually what is the most convenient case is that there is no, the body is infinite, which means that there is no boundary. Okay, so there are no boundary conditions. So in this particular case, if I have infinite body, I can say that this space of functions which are square integrable or with a finite energy on the whole domain, which means that they need to decay very fast in order to integrate to infinity. There are just, it is constructed of all constants plus I see when I got it wrong. Okay, plus all fluctuating fields on the infinite domain orthogonally with all fluctuating fields which are divergence free everywhere on the d-dimensional domain. And again, without boundary conditions. All right. So if I have infinite body, there are, I do not need to specify any boundary conditions because this condition that I need to be able to integrate or average my field over the domain actually implies that the field is either constant or actually decays very fast as I go to this infinity, otherwise it would integrate to non-zero value, and hence these conditions are prescribed indirectly. And what I will try to do in the forthcoming lecture is actually to convince you that this is actually what we want at the end of the day, to have really the homogenized, the effective or homogenized properties to be independent of other parameters. So basically the calculations in the spirit of Maxwell, Rayleigh, and Einstein were done on infinite bodies, which of course is very difficult by computational means, but analytically actually this is nice because we do not need to take care about boundary conditions, which can easily turn to a nightmare. Okay, so this is the first command, and the second command, yeah, and sorry, but I also wanted to say that in this particular case, this mean value has to be interpreted in suitable way, meaning that I will just take my body and I will just look what is happening with the field on a window or increasing size, and I will compute the limit. Once those become relevant, I will just try to explain it a bit better. And the final remark, which I would like to say is that I did a lot of advertisement for saying that I'm interested in the stored energy densities and their complements because they carry some physical meaning. But well, what I a bit hid under the carpet is actually the interpretation of that scalar product or inner product, that integral I'm computing, which has the meaning of work like quantity or power And if one of these fields is actually not the one which happens in the real body, but some test values in mechanics, but perhaps also in heat transfer that I do not know, this is also associated with virtual. So you perhaps have briefly recalled what the principle of virtual work means. So, in my generistic viewpoint, this is just the scale product, right? Nothing else. Okay? And now, this Helmholtz type of decomposition, which says that actually if I take, for instance, constant field and fluctuating, it will produce no work, be it real fields or virtual. If I say that I have all curl-free fields and divergence-free fields, they are mutually orthogonal to each other, meaning they do no work. Again, let it be real or virtual. So this is, something which I mean by this particle expression. So if you again recall what you did with Milan, you started with some functional, then you wrote optimality conditions, or perhaps you call it differently, but this was what he was doing. And then you got some statement and you can interpret it in terms of this principle of virtual work. And here, these are the same objects, but just seen from more general perspective. And this also, implies that if you go to one specific field, well, this Helmholtz decomposition is also called differently, and the field is micromechanics or homogenization. So if you will ever work in this business, there is, a buzzword you will see many times repeated, which is called Hill's lemma, which actually says that the virtual work done by constant fields is the same as the work done by the fields which happen in the body, roughly speaking. But if you just translate it into this term, this is precisely it. So what I'm saying is that if in the literature you will see something which is called the Hill's lemma, you can understand it equally well by saying that in the sense of work, and for instance, elasticity, when this is primarily used, or strain fields, which are physically accessible, are orthogonal to divergence-free stress fields, so self-equilibrated. They do no work. So now if you do the splitting, you can actually show that what matters in terms of homogenization are these fluctuations and not the mean values, roughly speaking. Sorry, this argument is still not solid. I need to think it over. Okay, so this concludes the second part of the lecture, and now we need to move to the next one. But unfortunately, as you perhaps can see on my screen, I have only 9% of battery left. I was clever enough to bring the charger, but I was not clever enough to realize that actually this cord is too short. So I just need to go to my office to get this extension, I think this is called, and I need to start charging it. So for those who are online, there will be something like 5-minute break, I hope. And now I'm away from screen. So once I delete that, I'm back. Okay. So again, as I already announced, this basically closes the most theoretical part of the course, in the sense that we are really looking at some general relations. What I will use afterward will not be very concrete, but there will be at least some results over it. Again, this was all about structure of the harmonic equations, which is what I announced at the very beginning. I will be using a lot, and I didn't lie. At least, I take many hours of your life trying to explain what I mean by this. So now we will move to really trying to convince you that this was not a complete waste of time. So we will finally come to the main topic of this course, which is called homogenization. And what I would like to talk in this part, which will be a bit more concrete, but still not sufficiently concrete to compute something. This is something I will do afterward. Is so-called, the notion of so-called homogenized apparent and this apparent is very fancy word. I have to learn. So in Czech, this is danlivý. Although, I mean, the chances are good that with your generation, you already know that. But this was not the case when I was at yours. And affective properties. Yeah, so just to position myself, we are we have really some nice repertoire, at least from my viewpoint, nice, of the available techniques. So in the first set of lectures, I was very much concerned with this PDE perspective, this differential equation perspective, where I presented this primal and dual problem. Then I completely swapped my argument, and I started to convince you that actually what is the nicest thing is this variational principle viewpoint, so variational perspective. And again, I introduced the primal and dual thing, so primal and dual. And other terms which I used was this Helmholtz, or was related to this Helmholtz decomposition. Which in the context of homogenization actually very nicely aligns with using this mean fields, this average fields and the fluctuating fields. So average or mean and fluctuation. Oh my. Okay, so this is what we have at our disposal. So what I would like to do in this lecture is to try now to unify everything, to put all this knowledge together and actually go reverse in time in a certain sense and justify why I spent so much time on this. Right? So what I will do is that now I will try to explain what I mean by these homogenized properties. What I mean by apparent and effective and things like that. You can see how this opens. And I will just proceed in these two lines. So now I will actually tell the same story 4 times. So I will first start with this primal PD perspective, which I will call just this primal governing equations. And in this primal governing equations, I just need. So for that, I need again to draw this this 4-component scheme. So, well, no, sorry. Just keep it here, but what I will present first on the right-hand side is the following. So I will assume that now I'm talking some heterogeneous body. If I had the handouts ready, then this body would be somehow, associated with a certain gradient to show that really the properties vary from space to space. And what I imagine is that this body will be located in a fictitious situation where I actually prescribe this capital E, which is not a function or its constant field, if you wish, but this is just d-dimensional vector. And for the reasons which will become apparent as we will progress through this lecture, this is something which I will call average or mean, macroscopic, but this is reserved for the very last part of this lecture, intensity field. And the argument is as follows. So if my body were homogeneous, so the argument is that if my actually L as a function of x is not L as a function of x, but is x is independent, it's x independent, then actually if I just prescribe this mean, average, and intensity field in each point of the body, this would be the solution. So if L is x independent, meaning that the body is homogeneous, not heterogeneous, but the opposite, homogeneous, then indeed my solution of my primal problem is E, right? So, for instance, assume that you will take, some finite sized body and you put it in the environment which actually makes sure that in homogeneous, just imagine that you will take this body under consideration and you put it into a certain environment in which there is a constant temperature gradient. So if you put the body there and just let it evolve until it reaches the steady state kind of behavior, this temperature gradient will be same everywhere, right? Okay? So here, there is nothing additional to solve. But if you have a body which is heterogeneous, then actually because of this heterogeneity, some parts of the body, they are better conductors of heat, or they are stiffer than the other one. And hence, even if I provided a body with this uniform background kind of field which it likes to follow, it will not. These heterogeneity will cause some local fluctuations, and homogenization is nothing else than characterizing or estimating these fluctuations. That's pretty much it. Okay? So what I mean by this argument, which is perhaps not the sharpest one, but the best one I'm able to give, is that if you have a look at this 4-component diagram, that the homogenization problem to solve is as follows. So you assume that you have certain given field ERD, so again, we are assuming that if this body was not heterogeneous but homogeneous, it would be in a state of constant temperature gradient. But you know that as a result of heterogeneity, this is not true. Because you know what the mean field is, the thing you are mainly interested in is fluctuation. This fluctuation is the original field from which I subtract some constant. So if this original field was compatible, was curl-free, adding constant changes nothing in this argument. So this fluctuation still needs to satisfy this differential constraint, so it needs to be curl-free. And on top of that, it must integrate to 0. I can connect these two things by the primary coefficient, and the flux which I will eventually get will be this J of X, and this is something which needs to actually, if I take the divergence, it goes to 0. The only thing which I need to take into account that in order to get the equation right, I need to add this constant value of this prescribed or given gradient field to the fluctuation for which I'm searching for. So what I'm now trying to say is that what I need to do is to start with this E fluctuating as a function of X. I need to add the constant field on top to it. So this gives me the full intensity or gradient, if you wish. You multiply this by the coefficient L of X, you compute the divergence, and this is something which needs to give you 0. Okay? So this is basically it, where at the moment I'm really not concerned about boundary conditions. This is something which I will just throw at you. I try to make a connection and I will just realize that something is missing. So at the moment, now I'm assuming that this E fluctuating is located in the field which I denoted as E, fluctuating, the subscript of omega, which I would like to recall you can be understood as all functions which are of this original curl-free field, which additionally satisfy the condition that if I compute their mean value, I get 0 in here. All right. Okay. And because this is fluctuating field, this E prime, I would like to recall you that no matter what I do, this is orthogonal to all constant fields, right? So they are independent. So now, we will do the standard we will do the standard line of argument, which means that what is on the left-hand side contains unknown quantities, and all known quantities are transferred to the right-hand side. So now, I just need to make sure that I highlight what is unknown in this particular case. So if I just go systematically, this is divergence. If I made my homework assignment 1, I know what this is, so no need to highlight it. This L are given primal coefficients of my problem. This is something which needs to be assigned to me, right? So I just need to underline to have the nomenclature correct. This E is that given ambient constant field I'm imagining happening in the homogeneous body. So this is something which is also given. And the only thing which remains actually is this E fluctuating. So this is now the primary unknown, right? So what I'm saying is that this fluctuation, E fluctuation as a function of x can be solved using the following differential equation. So I have this divergence in here. Oh, and sorry, I need a moment to charge the pen. Obviously, I forgot to do it before the oh my. So what I will do is that here I have my primary unknown E prime multiplied by L of x and subject to the derivative. What I have on the right hand side will then be minus divergence of L of x multiplying capital E, this given quantity. And usually, I mean, for aesthetic reason, people like me like to actually have this minus on the left-hand side, something which is something like positive number or matrix or positive operator. But this is not important at all. Okay? So basically what I'm trying to solve using this differential equation is the following. So, you know, if the body so if I just now throw again this argument that perhaps was not very transparent, but I do not know how to start better. So if this body was homogeneous, really, right? So imagine for a moment that there is no x dependent. So this L is constant, right? So what this means is that on the right-hand side, I will have divergence of the constant matrix times E, where this L is just the square matrix and this capital E is actually a column of D variables. So this is constant. So no matter what I do, this would be actually 0 on the right-hand side. Here I will have divergence of L of x, which would be L, just nothing else. So constant times E prime as a function of x. And now if you throw the argument, you need to have this, in order to this condition to hold, then actually the only thing how to, let me think for a moment. So if you just think it over, then actually the only condition how this can be satisfied is that this actually E prime is just constant, right? Because the only other way how to satisfy that, if you just imagine that you are just taking this derivative and applying it to this E, would be that this is divergence-free field, but we know that the divergence-free fields, these are precisely orthogonal to the one which are solving. So it actually turns out that this E is constant, and the only constant field which integrates or averages to 0 is 0. So this implies the, you know, if I had this hypothetical situation where the body was homogeneous, then actually if I just assume that I have this ambient constant gradient field given as a part of my problem, there are no fluctuations needed to satisfy the differential equation. So there are no fluctuations at all, right? If this L of x would be position dependent, it will, you know, be smooth function or start to jump, then I have to properly, interpret these derivatives, but you know, this can be done. Then because of this space varying property, this E prime or E fluctuation will be non-zero. It will encode the heterogeneity pattern, and eventually it will also encode some mean or homogenized properties. And that's it. This is the only thing which I need to do if I would like to homogenize. I need to find out this E fluctuation. So, you know, when someone or when you present this story for many people, for the first time to several people, then at least in my world or in my experience, there are some people who are really picky, who are really clever and say, okay, so I would like to solve this equation simply by saying that my primary unknown actually is E. It cannot be this E because there is this sign difference. So the claim these people, people usually make is, okay, so I will say that this E prime is minus this value, so this sums to zero, and hence the equation is satisfied, and I solve my problem. Okay, so what is the catch? So what is the wrong with this argument in particular? So I would like to remind you that, you know, this E is just constant, given constant field which I'm imagining to be present in my body. This E prime is in this zero mean chiral-free fields on omega, and these two are mutually orthogonal, so they are independent. So there is no way how I can compensate the mean field by something which is chiral-free and fluctuates on top of that. So this E here, this E prime, this E fluctuation, is actually something by which the heterogeneous body tries to minimize, in a certain sense, this deviation from zero, right, in order to meet this equation. And this compensation actually is caused by this varying properties inside. So you can see that, again, this fluctuation is a compensation which you put on top of this E, this mean field, this constant field, in order to satisfy the governing equations. Okay? And in order to get some reasonable unique solution, you must make sure that you will just search for the solution in the range of functions which actually cannot precisely compensate on what is on the right-hand side. So this is one possible explanation. Yeah, and I have 6 minutes remaining. Yeah, so what I wanted to say that, you know, this is one viewpoint, which actually can be made even more transparent using this variational viewpoint. There, this is visible in a much clearer way, because then I have some natural way how to, you know, understand how my system behaves using energy. So this can be also put in very nice energy-based argument, what this E prime actually tries to do. Okay, so any questions, remarks? Is this clear, at least to some extent? Okay, so now, you know, you may already guess what I will do with 5 minutes left only. So now I will say, okay, I will now consider the dual case, if this pen allows me to do so. So I will just prepare briefly the sketch here. So in the dual case, this is something which at least for me is a bit easier to understand or imagine. So I will just imagine that I have my body under question. Again, some weird potato omega in here. I'm now assuming that I have certain heat flux, which I will Now, imagine that actually, this heat flux is present in any point inside the body. If this body was homogeneous, so this L would be independent of X, then this was, this would present the only solution to the problem under question, meaning that the flux is the same everywhere and is equal to this particular quantity, because if this L is constant, then oh my. Here I have this dual coefficient, I apologize. So if this m is constant, that is m times j, which occurs in this differential equation, is constant, and if I compute its curl, constant of curl field is 0. So this is the only solution, but if this coefficient becomes x-dependent, in my language, if the body becomes heterogeneous, that this is no longer possible. And what I'm searching now for is the following. So, as you may already guess, my primal quantity now would be fluctuating part of the displacement field, because I have this given background macro flux field, or sorry, mean flux field, parents. I know that fluctuation is the original field corrected by mean. So if the original was divergence free, this one is as well. I know that if I combine this quantity with this fluctuation, I will get the full flux field, which I can take, multiply by the dual coefficient to get my intensity field, which has to be curl free, to make sure that I have a physically good solution. And finally, the equation I'm searching for is as follows. So I have this curl or rotation of my dual coefficient, which is possibly x-dependent, multiplying the fluctuation of my flux. And what I have on the right-hand side is precisely the same beast. So curl or rotation of the field, which is obtained by taking these dual coefficients and multiplying them by j. And again, this poor guy would like to be minus j, so it would also like to be constant. But he actually cannot, because it is just located in an orthogonal component.